Okay, well, it's 1 o'clock, so we're going to get started, and folks can keep joining us as they get in here. But in the we want to be sure we get this in a timely fashion. So here we go. But want to welcome everybody. Hope everyone's having a great summer. Hard to believe it's almost August. It's just flying by. But here we are again on one of our monthly webinars. Today we're going to be talking about, or Greg Folts with Marshall Institute is going to be talking about PM optimization, delivering value-added maintenance. So we're really excited to have him with us. Before we start, just a little bit about UE Systems. So for over 40 years now, we've been providing ultrasound solutions to facilities all throughout the world. All different kinds of applications, everything from ultrasound assisted lubrication to compressed air leak surveys, steam trap surveys, all that good stuff. So in addition to that, one of the things we really pride ourselves on is being able to provide content, resources, and just kind of be able to educate folks in the field of reliability. So these webinars are a great venue for doing that. And we've seen Greg present at several events throughout the industry, SMRP, at our conference a couple months back we had him, and just a really, really great presenter. So we thought we'd bring him in and talk to you all a little bit about PM optimization. So we're excited about that. Before I get him started, just some housekeeping. We are recording this, so if you have to pop out early or there's someone on your team that just couldn't make it, we will have this available for you all to view and learn from at a time that's more convenient for you. So you'll just keep an eye out on our website for that, and we'll have that up there. You can also find all the other webinars we've done and just use that again as another resource for yourself. You can ask questions. We highly encourage that. It's hard to make this completely interactive. We're all spread out throughout the globe, but you can type in questions, and I'll be asking Greg those questions as we go along, if it makes sense, if it's something he's specifically talking about, or of course we'll have some time at the end as well. So feel free to ask those questions, and we'll get as many of them answered as we can. And with that, I am going to turn the screen over to Greg. Give us 1 second as this handoff takes just a moment, and we'll let him get started. So Greg, thanks again for joining us, and show's all yours.
All right. Thank you, Maureen. Appreciate the introduction. My name is Greg Folts, President of Marshall Institute, and I'm excited about being here. I think it's a good group assembled. I was looking over the list of folks that are here, and it's pretty exciting to have a chance. So today we're going to talk about some PM optimization, and I think there's a couple topics that we want to hit on here. Let's talk a little bit about what it is to optimize our PMs and how we can really make sure we have value-added PMs strategy, and what's wrong. What do we typically find that's missing with a typical PM strategy? Talk a little bit about the task optimization itself, and a little bit about some steps or some things. I hope that I can give a couple of things that you'll be able to go back and do as a result of this discussion that we have. And then if we get a chance, I want to talk a little bit about the bigger picture side of this thing, optimizing the entire PM process, because I think that's a missing element a lot of times when we talk about PM optimization. So like I said, I'm with Marshall Institute. We've been doing a few things with UE over the past few months here. It's been great because both our businesses have been around for a long time. We've been in business for 40 years as well. We've got some legacy back to the early origins of TPM, and if you kind of fast forward to today, we are asset management. We help folks with PM optimization. We help them with setting up just overall asset management strategies to make sure that they've got the right practices for taking care of their equipment. And we do that mostly in the U.S., but we certainly, our clients take us all over the world as we go forward. And that mostly involves maintenance strategy, maintenance planning, setting up the key systems for maintenance, training and coaching folks that are going to be going forward. So, and that ultimately takes us into PMs, and PMs is such a core piece of what we do in the maintenance workflow as we go forward, that it just turns out that it's just something huge we want to be focusing on. So as we go forward here, like Maureen said, if you have questions, just shoot them to her, and she'll forward the questions on. We'll hopefully get a little bit of time at the end to answer any questions that folks might have as well. So PM optimization. It is not hard to get me talking about PM optimization because I just believe it is a core principle relative to our maintenance groups. And as far as myself goes, I was a maintenance technician, electrical, started mechanical, moved into electrical field. So I worked in a maintenance department. I helped execute PMs, at a task level out there working on equipment. And I saw, as I got into consulting and improvement, first at SKF Bearings, I was a maintenance technician there, went into TPM, driving the TPM process. Later on, got involved with the overall continuous improvement process. And so it was easy for me to recognize that one of the places that we could improve our PMs was that we had lots of opportunity to improve our PMs and optimize and make them more value added in terms of how we execute them. So the PM optimization process is based on the principles of reliability centered maintenance. We're not going to have a lot of time today to go into that, but there are some fundamental core strategies that come from RCM, reliability centered maintenance, that really help us to improve our existing maintenance programs, as well as if we've got a new asset that we don't have any knowledge about the history of failures on. But PM optimization is basically going to start with an existing PM program that's going to start with existing failure history that we have. Now that failure history can be formal or informal, meaning you might have a computerized maintenance management system that has all the history for 5 years in the system, or you may have very little data available. We can as we're looking at it, we can look at it from both perspectives. But the bottom line is we've got an asset out there that has a history of problems. It has a history of PMs that we've executed. It tells us about ways that the PM strategy has either been very, very successful or has gaps and has some non-value added activities that are happening in it. So when we're looking at PM optimization, what we're looking at is improving the effectiveness of the reliability strategy that we're putting out there. And so looking at the current PMs, looking at failures, and this idea that comes from RCM about managing the consequence of the failure, managing the risk that we're incurring when something breaks down, or the probability that it'll break down, and make sure that we have the best strategy for addressing that. Also, we're looking at the efficiency of the PM strategy or the reliability strategy as we go forward. So effectiveness means, is this strategy doing what it's supposed to do? Is it helping us to manage those failures, reduce the amount of failures that we're having, manage the risk associated with those failures? Efficiency means that we have the best value-added execution of that strategy that we've got. We've got the right resources, the right tools, the right access to the equipment, those kinds of things to make sure that we're efficiently performing our PM task. I can tell you, as a maintenance technician, there were lots of inefficiencies in how we approached our PMs. I worked at a few plants before I landed at SKF, and those plants often did not allocate the right resources, the right time, the right tools to executing the PMs to end up with a effective process overall. So we want to make sure. So when we think about what's wrong with our PM process today, or probably a better way to say that is what's not value added about the PM program. One thing we've got is that inadequate descriptions. So we have PMs that say check, inspect, and they don't often give criteria. They're worded too poorly. They're too short. They're incomplete. They don't give the information that I, as even a qualified technician, need to go out and perform that job effectively. So many PM tasks are done too often. You talk to folks executing PMs, and they're going to say, it says to lubricate that every day, and I know that's way too often, or it's not done often enough in some cases. So we've got to get that PM frequency set right. Sometimes we have tasks that are assigned to the multiple people doing the same task, and like anything else, if you don't have a single accountability, responsibility, it's a higher probability it won't happen because I thought you did it and you thought I did it. And then often, and this is the big thing that a lot of times you'll see, and if you're out there running PMs today, you've got these cut and paste from quote, quote, similar equipment, that it ends up that there's certain parts of the PM task that don't even apply to the asset that you're looking at. So we've got many things that cause PMs to not be value added. So all of that stuff kind of combines together to say that we end up with PMs that really shouldn't be in the list of tasks for this asset. Sometimes we're being too intrusive, we're tearing things apart when it'd be better off just left alone or using a non-intrusive inspection technique. There could be other technologies that might make it more practical. You know, the folks at UE might have a better way that we can look at that heat or bearing or vibration or sound or whatever it would be. So a lot of times we find that we're not really doing the PMs to the schedule that we've got. So I could have a really well-written PM task, but it's just not being done. It's a low priority. And a lot of times there isn't accountability for the quality of the PM. So we don't really get the follow-up that we need to have happen. We don't treat PMs as the most important thing we're doing. It's somewhere often much, much further down on the list, and so we don't get the improvement that we're trying to get for our process. So we're often putting a lot of effort and not getting enough gain in return from that. So so what we find when we look at PMs is that often we're moving PMs from, you know, a time-based replacement to some kind of condition-based activity, some kind of we'll do maintenance based on condition. We find that we can, because they were cut and paste and lots of other things, reasons that PMs might have got in there, there's some that could be eliminated and have no harmful effect on the machine. And by the way, it's really the technicians, the electricians, mechanics, craftspeople that are performing the PMs, as well as some input from operations that really will help us to find those tasks that really could be stopped without harming the machine, harming the reliability of the asset. Improving the effectiveness and extending frequencies of some of those PMs. So sometimes we find out that we just don't do them well, and we could do them less frequently. So that's certainly a case that we find. And then we find often that there are PMs that need to be added because we have failure modes that are happening on the machine that are not being covered by the current strategy. So a little later on, I'm going to show you some information on just kind of conceptually how to look at those questions that we see, some of the problems or non-value-added aspects of a typical PM program. The chart that I've got up right now, you know, we've done literally hundreds and hundreds of the workshops and help people set up for having a more effective PM strategy. And there's sort of a rule of thumb that you can think about, you know, 30-30-30. So 30% of the PMs in a typical PM program, if you got something that's been out there for a number of years, are often going to just be deleted. And they're going to be deleted by the folks who do them, knowing that that does not harm the reliability of the asset. About 30% of them are the right things at the right time, and, you know, generally speaking, they'll get spruced up a little bit and maybe modified a little bit, but they're in large part correct the way they exist. And there's about another 30%, just kind of rounding things off, that are you either extend the interval on or reduce the interval or add an entire new task for something that didn't. This 30% ends up having some pretty major modifications to the PM program. So I'll show you an example in a little bit of one that we did. It doesn't follow this exact model. I mean, the real world isn't. But a good rule of thumb is to think about the fact that if you haven't put some intense focus on your PMs, you've got opportunity to improve them, and you've got resources in your plant that are able to help you with this journey. You just need to think about some methodology and some principles. So thinking about how we would optimize those tasks. Again, I think any plant that we go into, what we find is that the people that are running the equipment, the people that are maintaining the equipment, they're probably more knowledgeable about that equipment than anybody else. They know that particular machine and its intricacies and problems and history. They knew that it was dropped off a truck as a young child or something. They understand what the history of that machine is. Now we want to pull data in when we're thinking about the workshop and the people that we're going to pull together to look at this. You know, the drawings, the manuals, We generally go out and take some pictures. We want to get the failure history available for us to use. We're going to think about, when we're talking about PM optimization, consequences of failures and failure modes. We're going to think about how feasible is it to do this particular PM that we've got in front of us. I mean, so sometimes there's a really nice, logical PM, but you could not do it at all. And I've certainly had that in my life. I've had examples where basically I've been asked to do a PM. I used to have to do a PM on a DC drive, and it had 6 brushes around the outside. And I could get at 5 of the brushes and check the length to make sure it was within specification. The 6th brush was right up against the frame of the machine, the back panel of the machine, and I couldn't get at it without dropping the motor down. So it was not technically feasible in the amount of time that had been allocated to do that task. And then secondly, I didn't have criteria, because when I would go to do that check in this particular plant I worked at, I didn't have criteria on the PM as to what the actual brush length should be. And so I'm trotting off to the storeroom, inefficient, to go find out how long a new brush is. And I usually wrote that on the motor, but it turns out that there's lots of inefficiencies, lots of ways that we can improve the way we do PMs. So think about a workshop, think about utilizing the folks that just have all that good knowledge about your plant, your machines to move forward. A lot of times when we're doing a PM optimization workshop, it's a quick win activity that can really get a lot of people excited about, hey, there's a lot of opportunity to improve our plant. Again, the folks, the craftspeople, the operators, the engineers, the planners in the organization, the folks that deal with this equipment every day, they have a lot of passion around wanting the equipment to run better, but not necessarily the forum or the tools to be able to go out and make that happen. So I know as a technician, what I found a lot was I would see lots of opportunities for machines to be improved. I would see lots of opportunities for PMs to be better. I might write, like that particular brush example I was talking about, every time I did that PM, I would write, cannot get at the 6th brush, and it would come out unchanged every time it came back out, right? So, now look, the first time I was put on a team and commissioned to drive some optimization, I mean, I was sticking my hand up saying, hey, I can show you one right now that is creating a risk for the organization, that we can't get at this thing, we can't do it in the amount of time. And we got together and we were able to cut an access panel in the back and be able to get at that brush. And the 4 hours that it would have taken me once to pull it off and change it and put the motor back on and realign the servos and all that, we were able to just do an alternate, cut an access door, seal it up, bolt it up, and now there was an access way to get at that piece of equipment to be able to do that. So those are the kinds of things that your folks on the floor are going to be really well tuned into to be able to drive PM improvement. If you take a look at kind of the how, and we'll spend the rest of the time talking a little bit about some of the how we can do things. So what is PM optimization? PM optimization is using RCM principles to try to find the most value-added maintenance strategy for a particular asset. PM optimization is using the folks that know those assets so well to come up with improvements and creating an environment for that to happen. When we talk about why we want to do that, number one, it's always the biggest gain in an organization to have availability increase in the equipment. The biggest gain is on the production side. So if you can find that key asset that needs to run better and apply PM optimization principles, make it run better, reduce the downtime by 50%, or have some significant impact on its ability to run, you will be contributing value added to the organization's bottom line. And so those are the kinds of things that we as maintenance professionals really need to be focused on as we're moving forward. So the chart that's in front of us right now is just kind of a high-level picture of some of the key things that we're going to do. And so if you're sitting out there today and you're thinking, okay, how do I start to approach this? A couple tips for you to think about. I'm going to come back and talk a little bit more about a couple key concepts from RCM. We could spend 3 days talking about RCM, but we're going to start at the left. We're going to take the failure data that we've got and the existing PMs that we've got for a particular asset, and we're going to define failure modes from those two data sets that we've got. So the real question is how does this asset fail to perform the function that it's supposed to do? And when we start to think about that, we start to get down into components and failure modes that we would see that are likely to occur. And in a case of a real live machine, we get down to failure modes that have occurred. We have in front of us at your plant today PMs that you're executing. So we know there's a strategy, there's things we're doing trying to prevent failure, and then a list of failures that are happening. And in those two data sets exists two pieces of information. Number one, the failure data shows us gaps where the PM strategy is not completely helping us to manage all the failures. So is there something that we could do better in the PM strategy to manage those failures? And then two, in the PM data set itself, it shows us the failure modes we anticipated that we should try to prevent, or somebody anticipated we should try to prevent as we go forward. And then once we get that list of failure modes, RCM principles teach us about things like the consequence of failure, failure patterns, and this thing called P to F interval. And if we take those three concepts, and I'm going to touch on those three concepts here shortly, that can result in a much improved maintenance strategy for our asset. And of course, we want to apply continuous improvement to that as we're moving forward. So this chart comes from RCM, and I don't have anywhere near the time to cover all of the information and the history that's in this chart, but there's a couple things that are in this chart that are really critical things to look at. I mean, there's just two major points of information we can pull from what are known as the 6 failure curves that we get out of RCM. And that is, and as a technician, I know this is truth. Age-related failures occur, and random failures occur. Now we're going to combine this information with some other facts in a second here, but basically bearings wear out over some period of time. And if we think about a bearing, it's got a wear-related curve that it's going to have. Maybe if we're looking at a set of them, they could follow, A or B failure curve here, where it's not likely to fail in the first 3 years, and then as it gets 3 years old, the likelihood that 1,000 of these bearings would fail is much, much higher. And then when we think about things on the right side, we're talking about that there are random failure modes in life out there. And those random failure modes tend to be things that we can't really predict they're going to fail, right? So the ones on the left we can predict based on age they're going to fail, more likely to fail as it gets older, and the ones on the right we have no ability to predict. And an example of that would be, I just unfortunately had this example, rock flying up from a tractor trailer, 4 car lengths up in front of you, and you see the stone pop off the back of the truck, you see it bounce and hit the roll, and you literally watch it come up and hit you in the window, and you have no ability, it's random, and you have no ability to act before that thing gets in there. We're gonna talk about that timing in a minute, but that is a random event. A flat tire, you hit a nail on the side of the road, that's a random event, whereas the tire wearing out due to age is an age-related event, much more predictable. So you can get a lot more depth out of these A, B, C, D, E, F curves, but if you just boil it down to age-related and random, there's a huge amount of value in that. So park that side of the information for just a second. We're going to come back to it. The second thing that we tend to look at when we're thinking about PMs and some of the ideas that we pull from reliability center maintenance is this idea of P to F curve, and many people have seen it before, but essentially a component, if you take my tire in my car, it has an age-related failure mode that I can, from the chart previously, it has an age-related failure mode that I can think about, but it also has the fact that once it starts to fail due to wear, there's a pretty long curve between when the initial signs of wear start to show that I should be concerned about, that's showing that signs of wear happening, and it actually gets to the point of failure due to that wear. So I have a long window. I could probably drive my car in the way I drive it for 6 months or more, probably, if I want to be foolish, between when it starts to show signs of wear and when it would actually fail to perform the function. And so that time is going to be really important in terms of our PM strategy and how we would approach PMs. So if we take those two facts and put them together, we get this really cool quadrant box that is up in front of you right now. And this quadrant box tells it combines those two things together. So think in the context of I've got a PM, I'm not sure if it's effective, I determine that the failure mode I'm looking for is age-related, looking for wear on the tire. That I could come into this quadrant box and I could help to determine what the best strategy would be for addressing that. So if we look at this, random failures and age-related are on the left-hand side of the over here. We've got the failure pattern. So we've got our age-related, we've got our random over here. Down across the bottom, we've got that P to F curve that we're talking about. Some failures have a very gradual curve related with them, and other failures happen very suddenly. So if we combine the two things together, we start to look at that a random and sudden failure is going to be a real problem for our PM strategy. In fact, it's most likely, when you're talking about random and sudden failures, you are probably going to end up running that component to failure. A good example would be a flat tire. Basically, when you get a flat tire that you hit a nail on the side of the road, it's a random and sudden failure mode, and our strategy is exactly that. We have a critical spare that we carry with us in our trunk all the time because we know that you can't inspect for that. You can't change the tire to prevent that. When we start to think about failure modes that are still random, but they have a much longer curve to be able to observe the deterioration happening. And you can think of an example of this would be a slow leaking tire. It's random when you would get one, but you have a gradual deterioration curve on it to where you have lots of time to respond to that slow leaking tire. In that case, these random and gradual curves are ideal places to be using in condition-based maintenance. In fact, they're the only strategy that you can use. If you have a time-based strategy to replace and completely eliminate slow leaking tires, it would probably not be an effective strategy. It's a random failure mode that has a gradual P to F curve on it. So we use inspections, we use condition-based tools to help us in that box. When we get up here to age-related but sudden failure mode, so you can think about a battery is a good example. I used to live in the north, and all our batteries when I lived up in the northeast died on the coldest day of the year. And I now live in Raleigh, North Carolina, and our batteries die on the hottest day of the year. But there's a failure mode in a battery that once it gets to a certain age, there's a sudden deterioration that begins to happen on it. And I've learned at age 56 that I am going to change my battery the first time it cranks slow. I'm going to go out and check a few things, but I'm basically, when I get that first sign that that battery's going bad, I know that the curve is coming pretty quickly. So if that was a very, very important component, if the consequence of failure was high, and we're going to touch on that here briefly, I would change it based on what I know that life expectancy to be. And then when we get over here to the age-related but gradual, so this one is age-related and gradual, we have a choice between time-based. So this is a great box to be in because when we're over here, we can either do time-based replacement as our strategy, or we can do condition-based maintenance as our strategy. And we can do that based on cost, right? So we can look at the cost, the dollars that we're spending here, and we can say which is going to be the most economic strategy. And of course, many times condition-based is going to be more cost effective than time-based, but not always, right? So we can look at the cost equation and make a determination on the best way to manage that failure. So now all of this is going to be pretty much tempered by this main thing that we've got to think about, and that is consequence. So when we're back here, all of these strategies are affected by the consequence of the failure, and that's another thing that really comes in from RCM. And when you think about consequence of failure, just think about, I have kind of a rule of thumb that I keep in my back pocket, and that is, you tell me how bad something hurts the plant, and I'll tell you how much focus, standardization, money I want to spend to alleviate that failure. And then I'll look at the quadrant box and I'll say, well, what can I do? It's random and sudden. Boy, if it's high consequence, I better have if it's an airplane and the airplane's going to fall from the sky, I better have yet I have a random and sudden failure mode I'm trying to prevent. I have to have either a critical spare ready to go, or if it's an airplane flying up in the sky, I've got to have a backup system in place to kick in when that first one kicks out. So I reduce the probability that random and sudden failure mode will impact my plane by having, I've been on a plane that lost a hydraulic system, and I'm really happy when that random and sudden failure mode occurred. They had not one but two backup hydraulic systems that kicked into place. So we can take the consequence of failure, something very important, and determine what is the best strategy, time-based, condition-based, spare part, run to failure. What is going to be the best strategy for helping us to address that? And the reason, in a lot of cases, we have non-value-added maintenance strategy, PM strategies, is that if the consequence is very low of a particular failure, we might be spending way too much money trying to avoid a consequence that doesn't matter much in our organization. So consequence helps us to understand how much we should be concerned. And you can think about your risk on any particular failure mode that you're talking about is really the probability that it will occur times the consequence of it when it happens, and were it to happen, right? So something that has a high probability and a high consequence, your risk is very high. Something that has a low probability of occurring, low impact for it to happen, your risk is really low on that thing. So that should tune how much we spend, how much we focus, how much we standardize, how much we really drive avoiding that particular consequence of failure. So managing that failure. Now, when we think about the PDF and the failure pattern, the bottom two bullets here, they help us determine what we can do. So consequence says, what should I do? Do I care? How much should I spend? And then the two bottom pieces, PDF and failure curve, kind of wrapped up in that little 4-quadrant box we were looking at, helps us to understand what's an effective way to manage that particular failure. This is a result from a PM. This is a real PM optimization workshop, and in this particular machine, we had there was a 6-week downtime over the course of a year to run it. They needed more parts off this machine. They could take every minute, and so the tendency of production was to cut the PMs and not do the PMs and skip the PMs and all that stuff that tends to happen. And so we were able to really go in and use this tool set to look at, do we have the right intervals? Do we have the right frequency of PMs? Do we have some PMs in here that don't need to be done? And in this case, do we have some PMs that could be done while the machine's running, done while the machine's up and running online, as opposed to having been done during the downtime that we were taking the machine out of production safely? And so it turned out that there was 87 hours of PMs that could be pushed to being checked while the machine was running. The previous philosophy had been, well, hey, it's down for 570 hours. We're just going to go ahead and do them while it's down. But it was important to say, no, let's find those things that we can do while the machine's running. Let's get those on a different list, and let's focus while it's down on the things that must be done while the machine is down. And that activity, and again, this was a team of folks who said, this is not a value-added PM, and this is a PM that we should add over here, resulted in $279,000 more production off the machine. There's some little bits of maintenance costs that are in, yeah, we spend a little bit less time doing the PMs, and there's some maintenance costs, but the big dollars are the production that we need to get off of that asset. So when you're thinking about PM, we tend to have, we call it review of existing maintenance as one of the variants of PM optimization that we do. And I want you to think today about when you go to do PM optimization, if you're sitting on there today and you want to take, hey, there's some ideas here I'd like to take and go move forward with. Number one, go get your data. PMs, go get your failure data, go get your OEM manuals, go take pictures, go visit the machine, go talk to operators, go get the operator logbooks. You got to get all the information that you can that's available. And if you have no information, if you have no data in the system, you still have lots of people who know lots about this machine. So go get all that data and assemble it together. So next we're going to review the current failures and PM data. So we're going to pull this in, and we're going to kind of cycle between 2, 3, and 4 here, where we get the PM data together, the failure data together. For each of those failures that we're seeing in the history, or each of those PM tasks that we have, determine the failure that we're trying to avoid and what the consequence of that failure is. Compare our existing maintenance strategy to that consequence that we've got out there, and see if there's an opportunity to add, delete, modify existing PM tasks or add new PMs in. And then I'm going to talk to you in the very end here a little bit about PM, optimizing the overall PM system. So a lot of times we get too focused on the tasks and we're not thinking enough about the whole PM process of how we execute PMs. But think about that a little bit, and then think about an action plan to drive the improved tasks. You got new tasks that are better, so you got to get them in the system. You got a better way of resourcing PMs. You're going to have to think about a plan to make that happen.
Hey,
again,
hey, Greg. Sorry to interrupt. Just someone had a question about that slide you were just on, so maybe you could pop back to that. They're just looking for clarification around the data that you're specifically talking about in step 2, the failure and PM data. So if you could maybe just clarify that real quick, that'd be great.
I can, and I think it's going to be easiest right here on this next slide. So the two pieces of data, thank you for that question, by the way. The two pieces of data are the failure data that you've got in your CMMS system and the existing PM data that you've got in your PM in your CMMS system as well. Now, we will get other data like operator logbooks and whatever else is out there, notes that people have, things that tell us about failure. But I'm trying to get a complete list of all of the failures that have happened on the machine and a complete list of all the PMs that we're currently doing on the machine. So, because if I understand the failures, when I look at it, I'm going to see that there's failures that we already have a PM in place for. So when I get those two main pieces of data in front of me, I'm going to say, oh, I've had a failure of the main shaft bearing, and I look at my PM, and there's a task out here to lubricate the bearings on the machine. I wonder if that's a good strategy, right? I got a real failure. I've got a generic PM task out there. I had that exact thing in a workshop a while ago, where we had 6 main bearings that were failing in the data history. We had about 60 bearings that were all in one task: lubricate the bearings. So it became very evident that in order to stop the failure mode from the bearings, I need to improve my PM task significantly. Okay, so one thing we get from the data, 2 data, failure data and existing PM data, is that it allows us to compare how well is the existing PM strategy taking care of the failures I thought they would take care of. Now, in some cases, we'll find that in the failure data, there's no PM out there for this belt that keeps breaking on the machine. And so now I've got to ask the question back to the Quadrant box, what could I do? Is this just a random sudden failure, or is this belt's wearing out? I really could be changing this belt on some interval, or I could be inspecting it for wear. When I have PMs that have no existing PM, we go through the process of looking at, could I, should I, does consequence of this failure do it? And a lot of times what we'll do with the failure data is, and if we had more time we'd go into a little bit more detail on this, but the failure data is usually ranked by consequence of failure, and that helps us to go to the top of the list and say, wow, if I stop these 20% top failures on this machine, and some of those top failures have existing PMs, but they're not very good, and some of those failures don't have PMs, and they could, then I'm going to make a huge difference on the reliability of this asset. And then when we get to the far end of the spectrum, we're going to have some PMs that have no failure data associated, and those PMs, we can kind of boil them back to what's the failure mode we're trying to stop on that. So the failure data, the PM data, turns into a large list of failure modes that we're trying to prevent, and the quadrant box, the PDF curve, and the age curves that we talked about all help us to determine the best strategy to manage that failure. And consequence is your biggest lever to determine how much I care and what should I do, how much should I spend in moving this forward. All right. So we're getting pretty near the end where I'm going to open up for questions here. But the last slide, I wanted to, one of the last slides anyhow, I wanted to give again, a couple of practical things you could go back and do. This next list of questions that's up here is, I've done some workshops where there wasn't much data. There was a PM strategy. You know, they had a list of things they checked on the machine. And we had a large group of folks, and we really were trying to get a lot of folks looking at PMs. And so we came up with this list of things that we could ask about the PMs. And so if we took a particular failure mode that we were trying to stop, a particular PM that we were trying to address, we could take a PM and we could say, what's the failure mode that this PM is trying to prevent? And then we could look at it and say, okay, is this task needed? Needed comes down to consequence, right? When I have this task to go out and paint the machine pink, and is that PM annual task that I'm doing something that's really needed in order for this asset to fulfill its value to the organization? So if the answer is no, then there's probably good, cause for removing this. If the answer is yes, we need this because there's a consequence of failure, this thing matters to the organization. Now there's this question of, is this the best task or the best method to use? So these questions that are up in front of you right now are things that you could ask just very simply about any PM task or set of PM tasks that you have for a machine. Do I need it? Is the consequence high enough to really be spending the time looking at this thing? Is it the best method? Could I do it with a predictive maintenance tool? Could I write the PM better so that it's better executed? If I could, then going on further, is this the only task in my PMs that addresses this particular failure? It's amazing when you start looking at a PM and the failure mode it's trying to address from just a general set of PMs that might be out there. What you find a lot of times is that there is no really specific failure mode that this thing's going after. Like the PM that said, lubricate all the bearings. Okay, yeah, in general it was trying to prevent failures of the bearings. But when we looked at the data and found these 6 bearings that had failed multiple times over the last 3 years in the data set, we could get very specific about the task, the frequency that we were going to do to prevent those bearings from failing again. We could come up with a very good task or method for making that happen. We could make sure that we had a task that was aimed directly at solving that failure mode. This generic PM that said, of all the bearings, I said, well, how many bearings are on the machine? And nobody knew. Okay, there's probably 60 bearings on a machine. Okay, so you really think this task that comes out and says, check all 60 bearings, and we're really technically feasibly doing that task? And that it was very stark to them that I got 6 bearings that are failing, this really generic task. Let's get down to a specific failure mode that we're trying to stop. And make sure there's only one task, one resource assigned to go prevent that failure mode. So if you've got operators and maintenance people first shift, second shift, third shift, all looking at the same thing, invariably what will happen is nobody's looking at it at some point. So you need a task, a responsible to look at it, and then is this the best resource for the particular task that we're looking at? You got different, in all the plants that are out there right now, there's 222 people out there. So you've got a whole different set of cultures and environments and unions and all kinds of things going into who's the best task to the resource. But what we look at, given the fact that there's certain guidelines within a plant, is who has the skill, who has the tools, and who has the time to be able to perform this task. Now, in some environments, I could answer that question and say, hey, the operator's got the tools, the time, and the skills to look at the oil level of the fill glass on the back of the machine. Now, maybe another question is, he or she going to fill it? But we just look at who is the best resource to do all the tasks, and of course you've got guidelines, the other guidelines that have to be applied in there. But from a pure value-added perspective, make sure this task is needed. Make sure it's the best way to perform the task, predictive maintenance, preventive maintenance, time-based, those kinds of things. Make sure that it's a single task with a single accountability, and make sure you have the best resource, somebody who's trained, who has the skills, the tools, and the time to perform that task when you're putting it together. So to me, like these 4 or 5 questions that are here, maybe 6 with the sideways ones, is just a really simple way to look at trying to optimize your task as you go forward. Now, you can use a tool, and there are various tools that you can get your hands on out there. So some of the stuff that we've done, we've done a lot of work with the guys from Australia, OMCS, and they've got a software tool that can be used for PM optimization. I have no commercial interest with them. I'm just saying there are tools that you can use. We have spreadsheets that we'll tend to use for smaller companies that just want to get some assets put in place. You can build your own spreadsheet that helps us to look at the consequence of the failure, the root cause, and what's the strategy that we're going to do to move forward. When we're working with clients on site, we have a little web-based tool that we give them access to that lets them do their PM optimization. But the point is you've got sharp people can put together a spreadsheet or put together some way to pull this together. And if you look at some of the criteria that's in here, what's the component of the main conveyor? What's the condition that we're trying to prevent the bearings from seizing? What's the severity, detectability, and occurrence? Multiply those together, this problem's a 108. And you get some problems that are 500s and some problems that are 100s and some problems that are 20s. You take the top of that list and you start saying, what can I do to prevent this failure? Looking at that quadrant box, you might find that there's a better PM strategy. Look, do you have a current PM? Like in this case here, PM number 234 is already in place. Oh, it's really generic. It doesn't have the criteria in there. So we're going to go out, get the criteria, make it specific, and improve that PM. And if you walk through your failures and you walk through your PMs in that way, thinking about how important is this failure that either the failure from your CMMS system represents or the failure that the PM is trying to stop, you will improve your PMs. And you've got the people and the resources to move that forward. Look, folks like OMCS or us, UE, folks can help you speed up how you're optimizing your PMs or you're doing things. But at the end of the day, you have to have passionate people who believe that this is something that's going to make a difference for the plant, that are internal champions for this change as you're moving forward. It's a pretty core piece. At the end of the day, you've got to have some kind of action plan to get these things implemented and moving forward. So it's just a simple spreadsheet on, what are we going to do and who's responsible and the date, those kinds of things. And again, you've got the ability to build these kinds of things within your plant. So last thing I want to mention, and then I'm going to open it up for questions, is that think about the bigger picture here as well. So we've talked a lot about efficient and effective tasks that you've got to have. To have an optimal PM process, that's only one piece of the puzzle. You need to have the right resources to execute the PMs, that have the right training. You have to have the right access to the equipment, so you have to have a partnership with production. You have to make sure those PMs are done to the quality that you've just built into the, you said this is a really important failure mode, making sure the main shaft bearing doesn't lock up on the jet engine. And you said, I'm going to assign Joe the resource to go do it, I'm going to give him access to the equipment, and then Joe has to have the right sheet in front of him to say, here's the specs, here's what I need to look for, here's what I'm going to do if I want to prevent that failure mode from happening, and then Joe has to perform it to that expectation that's on that sheet. That whole thing has to come together in order to have a really effective PM process. So the KPIs, key performance indicators, are going to be useful in helping to make sure we move things forward, and of course software is going to help us to move things forward. Last but not least is the fact that to improve your PM system, you can form a maintenance excellence team or a PM focused team. Get your cross-functional team of supervisors and maintenance technicians and operators, maintenance engineer. Do a gap analysis of your current PM system. Do you have the right PM quality? Do you have the right PM compliance? Do you have the right job plans? That task optimization is going to get the right what's to be done, how's to be done, what's the criteria for good or bad, what do you do when you find it bad, get your scheduling right, make sure you return it to service in a professional way. So get a plan for driving this activity forward. So in summary, what is PM optimization? It's a tool to optimize our PM strategy, make it value added. It relies on reliability-centered maintenance principles. The elements of a good PM process, we're going to make sure that we have all those resources and KPIs and software and training and time to do the task. All that stuff's got to be in place as we're moving forward. And we can apply some pretty nice principles from the 6 failure curves to the P to F curve, and you can find all kinds of writings on this stuff. So I'm not talking about something that I invented because I slept in a Holiday Inn last night. This is stuff you can go find all kinds of information on that will help us mash together and have the best PM strategy. And then when it comes to the steps, just make sure that you're getting your team together, you're relying on the knowledge of the people who do the PMs and the people who run the machines, and you're using some of those principles from RCM, getting your data together, and then just really going through the process, looking at each failure mode and what PM do you have, and could you have a better one? And when you look at the PMs themselves, what failure mode is that PM trying to prevent? All right, I'll open it up for questions.
All right, great. Yeah, sorry, I didn't mean to cut you off there. Yeah, no, that was great presentation. We've got actually some really good questions, so let's try and hit as many of these as we can. And if we don't get to your question, don't worry. I'm going to make sure Greg gets the questions that do get answered and don't as well, so he can follow up with you and get you what you need when we run out of time here. So let's just rock and roll. One of the first ones that came in was from a guy saying that he's in a bit of a unique situation. He's building a brand new plant and developing PMs from the beginning with no history. How does PM optimization come into play for him, since he has no history as of yet and only have the recommended OEMs to go off of? What's your advice there?
Yeah, so my advice there is, I guess, first of all, pure RCM, reliability-centered maintenance, deals with the idea that we would look at, what are the probable failure modes we might anticipate on this machine, and then use all the stuff that we were just talking about, the quadrants and curves and all that, to come up with a strategy. So you might lean a little bit more towards pure RCM. Secondly, when we hire people in plants, we usually have people who have experience with similar equipment, and they know how components fail. They know how assets fail. So I'm going to usually take the OEM strategy, vet that against the failure modes, the OEMs, because they're not very good at using this kind of philosophy in a lot of cases. So vet that against this kind of philosophy, come up with what I think the best strategy, and then optimize as we go along after the first year or so.
All right, and then this one's a little long, but I'll try and get through it here. Just kind of suggestions on actually writing the PM tasks or steps. So, kind of he's describing the battle between, you got the seasoned, experienced techs who are like, "Whoa, this is way too long, too much information," versus obviously you have new people coming in who might need that extra detail. So, is there a balance? Do you have any,
Yeah,
suggestions there?
the balance that is, I'm going to usually assume that I'm writing for a qualified technician. Okay, so they know righty, tighty, lefty, loosey. They know the basics of what needs to happen. What they don't know is how long that brush is supposed to be when it gets pulled out. What they don't know is what the torque value is supposed to be. What they may not know is you should replace lock nuts when you take them off. You shouldn't reuse them. So there's a whole set of things that are going to be really value added. And then I would just say to that person in that question, I find that I had a bunch of people when we were doing that bearing, 6 bad bearings needed to go in. They said, "We've got a PM. We know what to look for when we're going out there." And when we pulled the data, it said, "Oh, these bearings have failed 6 times in the last 3 years. Those are the bearings we should be looking at." And we pulled the PM. They sat there going, nobody could argue that check all the bearings was a rational way to make sure somebody looked at those 6 bearings. And so a lot of times the data will help to guide how that needs to happen. So and I mentioned it earlier here, one of the things to do is make sure that you're writing what's to be done, how it's to be done. I can't find it right now, but what's to be done, how it's to be done, what's the criteria for good or bad, and what do you do if you find it bad. Yeah, it's right here. So what's to be done, how it's to be done, and that's where you're going to get into, I don't need a Chilton's manual necessarily, but I do need some key steps. Make sure that you relieve the bottom screw before you take the top 5 screws off, because it's going to all spring out at you if you don't. Don't leave that to chance. Telling them all the details about this assembly, maybe not, but criteria. When you put it back together, new lock nuts, torque it, whatever the right criteria is going to be. And then another good thing is what to do if you find it bad. Primarily because you mostly want them turning these into corrective maintenance jobs. Sorry, go ahead.
Yeah, no, that's good. I have actually had a couple people ask the same question, so it seems like a good one to toss your way. What does RPN stand for on one of the tables that you had shown?
Okay, good question. So that comes from failure mode and effects analysis. So like from the quality circles, people are doing these FMEAs, and the RPN stands for risk priority number. So when we take, and I had some slides in here, but I just didn't have enough time to go into the detail. I took them out before the presentation that talk about, we usually get a risk priority number by multiplying the severity of the failure. So if I take, I had a flat tire on my car. So what's the severity of when that happens on a scale of 1 to 10? Is the first thing we look at. We look at severity, detectability, how easy is it to see that failure happening before the negative impact happens. So we'll rank that on a scale of 1 to 10. So severity, detectable, and occurrence, how often or probable is it for this thing to happen. So since it's reasonably probable that in the lifetime of the car you're going to have a flat tire, and it's very severe in terms of the function of the vehicle when you have it, and it happens very quickly, that ranking, severity times detectability times occurrence, would cause that to be a high-ranked item, would float to the top of my list, and I'd say, I'm not taking my spare tire out to put more luggage in. I want to make sure that those ones that have a high risk priority number have a very effective maintenance strategy on them. And if you look at your data and you rank it that way, you will find some failures that you have had in your plant that are causing downtime on your equipment that you will be able to come up with better PM strategies for. Guaranteed.
All right, great.
Or
Well,
your money back from the seminar.
yeah, there you go. All right. Well, like I said, there's a couple other folks that had some kind of specific questions, so I think Greg, it'll be best for you to reach out to them offline. So I'll be sure I get those to you. And just, since we are up at 2 o'clock here, I'm just going to take the screen back, and I've just got a couple closing slides. But Greg, thank you so much. Great presentation. We had great attendance. So obviously a relevant topic, and with all the questions that were coming in, obviously one that folks are pretty interested in. So we thank you for taking some time today to go over that with us. So just to wrap up here, uesystems.com, that's our website. That's where you'll find the recording of this webinar. I'll have that up hopefully before the end of the day. Also, all the other webinars we've done. So if there's other topics you're interested in, pretty much if it exists, we've probably done a webinar on it. So check out our website for that. Get on our LinkedIn group. That's a great place to take some of these questions. Some of you had, kind of some unique situations. Our LinkedIn groups are a great place to toss those kinds of questions out, get some feedback from your peers in the industry, just to get different perspectives. So use that, again, trying to keep everybody connected, even though we're all, spread out throughout. And then just a couple save the dates. So our next webinar, we're excited to have some guys from Amazon with us, and they're going to be talking about basically how they've entered the reliability field and how they're improving their distribution centers, and we're catching them. Oh, yep. So we're catching them right before they kick into the high season with the holidays just around the corner. So we're kind of their last commitment they could make before that gets crazy, but that should be a really good one. And then September, for those of you that have anything to do with STEAM at your facilities, we are turning September into STEAM-tember. So we're going to have a whole month of webinars related to STEAM, resources going out, articles, things like that. So we're getting steamed up for that, if you will. So stay tuned for more details, and of course our website, we've got our full training calendar there. So with that, I will leave our contact information up for you all if you need to get in touch with us. And Greg, again, Marshall Institute, you guys were great. Really appreciate it, and hope everybody has a wonderful rest of the day and a great next month until we see you all again. Thanks.
Thanks all.